Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that larger playlist, we create mini-series depending upon the experimental design that we're covering. In this mini-series, we're looking at analysis of covariance, and this is part 5 of a 9-part mini-series. This one's on estimability. Now, before watching this, if you're not familiar with estimability, I have a 4-part mini-series on estimability within this playlist. I'd highly recommend that you watch that prior to this. In the analysis of covariance model, it's a general linear model, but we partition the design matrix and the parameters into the ANOVA piece and the regression piece, or the covariates. All the covariates are centered. And this ANOVA can be any balanced ANOVA design that you want. One-way fixed effects, 2-factor analysis, 3-factor analysis, randomized complete block design, any balanced ANOVA. Now, ultimately, I want to discuss a theorem on treatment contrast. But prior to that, I have to look at theorem 1. We have to prove theorem 1, then we're going to use it in our proof about treatment contrast. Now, theorem 1 deals with the estimability of a linear combination of these betas. If it's estimable, then the L is equal to this, which is rho prime I minus mz x. This is for some rho, and where mz is the perpendicular projection matrix onto the column space of z. So it's z transpose z, inverse z transpose. And so I left off that little transpose there. Then the proof follows this. So first of all, we'll assume that L transpose beta is estimable, and then we'll show that L has to be of this form. And then we'll show if this is true, then it's estimable. So if we look at L prime, L transpose beta, it's equal to a linear combination of the bigger set of parameters, but the last piece is 0. Right? So if taking a linear combination of this, if we make the last one 0, which corresponds to this, then it's a linear combination of the betas. That's what we're saying here. Now, let's let lambda transpose be estimable. That means it has to be a part of the row space of the design matrix, right? We're going to show, yeah. So then, but this X star can be partitioned into the ANOVA piece and the regression piece. And then we just multiply the rho in. And as we know, lambda is equal to this. Right? So that says L has to equal rho transpose X. Now, if we add 0 to this, it doesn't change it. So rho transpose X is this. And notice this piece, rho transpose Z has to be 0. So this is 0, which means this is 0. So we've added 0. But now we can left factor out a rho and right factor out an X, and we're left with the identity matrix minus this MZ. And that's exactly what we wanted to show. Now let's prove it the other way. Assume this is true, and then it has to be estimable. Now, as a reminder, this is equal to this. So the linear combination of the betas is equal to lambda transpose beta star. Of course, where the last pieces of this lambda vector are 0, so it equals this. Now, by assumption, L has to be this, right? Now, let's add 0 to this quantity. So we come down, that's this piece, and then we add 0. So I minus mz is the perpendicular projection matrix on the orthogonal complement space. The column space is z. So any column in z, or linear combination of z, anything in the column space is z, times this is 0. And clearly z is in the column space of z. So this is 0, so we've added nothing. Now let's left factor out a rho I minus mz. And then what's left over is this, but sort of unmatrix multiply it, and we get this. So this says that lambda, now the beta stars are the same, and lambda is equal to a linear combination of the rows of column space of X star, right? This here is a row vector, so this is like a new row, it's a row vector. So this is part of the row space of X star, so it's estimable. And that's one of the necessary and sufficient conditions for something to be estimable. So since this is estimable, this is estimable. And the theorem is proved. Now, the second theorem is this. So here we have let y equal x beta plus z gamma plus epsilon be an ANOVA model where x is a balanced a balanced ANOVA without interaction terms. Now, if this is estimable, so in this ANOVA design, there are treatment effects associated with it. Now, there may be more than one. If it's a 2-factor ANOVA design or 3-factor, then there could be more than one treatment. But one of those treatments we can denote by the taus. And we're taking a linear combination of those tau parameters for that. So, the first treatment. Now, if this is estimable, then this contrast then has to be a treatment contrast, meaning they add to zero. This sums to zero. Now notice the x, that's this piece, can be anything. So there's a mu parameter associated with it. There's the x tau, so that's the space associated with the treatment of interest. And this is everything else. So if it's a 2-factor, a 3-factor, a randomized complete block design, this is associated with that. So it's a very general x0. Now the proof goes like this. So L beta, which is equal to L tau transpose tau, right? Where L is equal to this, right? Because in this beta parameter, there's the mu associated with this, Oh, that should be a 1 vector. What the heck? And then it's associated with the treatment. And then the last piece associated with the rest of the design matrix is has to be 0 because we don't want to pick up any of those beta parameters. So since by theorem 1, L has to equal this. That was according to theorem 1. But X is partitioned, and look, I used the right one here, is partitioned into 1, X tau, and then everything else. So then you multiply that times each of those, and we're here, right? But this is L, right? So this piece has to be 0, and we're assuming it's estimable, so this has to be true. L tau transpose is this, and this is 0. But let's look at this piece first. So let's set it equal to 0, which is here. Then let's multiply those in and then add that to the other side, and we get this. Well, MZ is the perpendicular projection matrix on the column space of Z, and it is this piece right here. But the columns of Z are centered. So when you add the columns of Z, in any column in Z, it adds to 0. And that's what this corresponds to. It says we're adding the columns of Z, right? Because we take that times this, and it's 0. Has to be, because they're centered. So one row transpose 1 is 0, and row transpose MZ1 is 0. Now let's look at this second piece. This has to equal this. So that's what we do here. But now let's sum these. Let's sum the components of these vectors. Sum the elements of L tau. Well, that means you just dot product it with 1. Now, this here this, in each row, there is only one 1 and the rest zeros. And that's true for every row, right? Now the columns, of course, there can be lots of columns with, a column with lots of 1s that correspond to a particular treatment. But each row, there's only one 1, the rest are 0. So when you take that times, you're getting 1. And then 1 and 1, 1, 1, 1. So you get the 1 vector back. Now let's multiply these in here. Or we could just do it this way. We know it's 0. Right? I think my logic was this. This is 0. Right? That's 0, and we're left with this, but then that has to be 0 too. But really, I could have just gone straight to 0. So thus, this is a treatment contrast. They add to 0. And that's what we wanted to show. Well, in the next 4 videos, we're going to do, I'm going to say examples. The next 2 are generic or general or abstract examples. And then the last 2 videos will be very specific examples using the R software system. Well, I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.